This problem is from 4.7 number 13. It says a roasted turkey is taken from the oven when its temperature has reached 185 degrees Fahrenheit and is placed on a table in a room where the temperature is 75 degrees Fahrenheit. So that's the surrounding temperature. Give answers accurate to at least 2 decimal places. And I have the correct answers here, and then I have the, so you can ignore the other answers. I just want to show the correct answers. That's what we're shooting for. So the first one is if the temperature of the turkey is 155 degrees Fahrenheit after half an hour or 30 minutes, what is the temperature after 45 minutes? And then when will the turkey cool to 100 degrees? So the first thing we're going to do is we have this formula, T of T equals A e to the KT plus T sub S. This is from the textbook. So that T sub S is the surrounding temperature, so that's 75. And it tells us that A is going to be the difference between the temperature of the turkey in this case and the surrounding temperature. So that's 185 minus the 110, minus 75 gives us 110. So we get this initial formula of T of T, so the temperature times T equals 110 e to the KT plus 75. Now, we want to know what that K is. We'll need that to find other information. So what it does tell us is that at time equals 30 minutes, the temperature of the turkey is 155 degrees. And I'm going with T being in minutes, and then I know the last question asks for it in hours. We'll just divide by 60 to get hours. So we take that 155, we're going to put it in place of T of T. So if it helps, you can say T of 30 is 155, which is equal to this 110 e to the K times 30 plus 75. And the only unknown here is the K, so we're trying to solve for the K. So E is just a number. Don't panic about that, and we can easily work around that. So I can subtract the 75 from both sides. And we'd have 80 equals 110 e to the 30k, if I can write it like that instead. And then I'll divide this by 110. So, and there's a part of me that wants to simplify that 80 over 110 to be like 8/11ths, but I'm going to leave it like this so I don't confuse anyone. I hope that doesn't confuse people. So we have the 80 over 110 equals e to the 30k. So we're trying to get this, again, this k, and so that's a power of e, so we have to do a logarithm base e, which is natural log. So I'm going to do the ln of 80 over 110 equals ln, or natural log, of e to the 30k. And we do that because the natural logs then have the basically inverse property of an exponential, exponential base e for natural log. Logarithms have the inverse property of an exponential. So we'd have the natural log of 80 over 110 equals 30k. And then we will divide both sides by 30. And we end up with k equals the natural log of 80 over 110, and that whole thing is divided by 30. And you get approximately, it's not pretty, and I saved this on my calculator for the following calculation, and I could just go up, hit enter, and that whole number, which is even longer than what is shown on the screen, gets put into the expression that I'm evaluating. So I have negative 0.0106151244. Now you could round that off, but you're going to propagate some more error. Even that's rounded off. T of T, it will then be 110 e to the negative, ready for this, 0.0106151244 t plus 75. So there's our formula. We can use that formula to find the temperature at time equals 45 minutes, which was the question for part A. So time at 45 minutes is 110 e to the negative 0.010615 244 times 45 plus 75, and I put that in my handy dandy calculator, and I was able to come up with 224 degrees. Okay. And that was the answer that we saw, 143.244. So the next part is they want to know how long before the temperature's at 100 degrees. So we're going to put that 100 is the temperature we're after, equals the 110, e to the negative 0.010615244 t plus 75. Then we can subtract the 75 from both sides. Again, we're solving for this t, and t is a variable that's in the exponent or power of e, which is the constant. E is the constant. 25 equals 110, e to the negative 0.010615244 t. And we can divide both sides by 110. Kind of the same process we did before. So we end up with 25 over 110 is equal to e to the negative 0.010615244 t. Then same thing, it's a base e, so I'll do a natural log, because natural log is log base e, so 25 over 110 equals natural log of e to the negative 0.010061544 t. And that has the property of that kind of canceling. The natural log undoes it, basically. Oops, wrong color. Oh no. And let's do this, erase the red, and we're on to blue. So we'd have the natural log of 25 over 110 equals negative 0.01061524 t. Divide both sides by negative 0.01061524. Divide that out. And our t equals natural log of 25 over 110 over negative 0.010615244. And that comes out to be approximately, let me get my calculator because I left it on my calculator, 139.5732911. I'm sure someone in the comments will argue, wait a minute, significant digits. And if we go to, I think they did 3, I took that number, 139.5732911, divide that by 60, because 60 minutes in an hour. And anyway, minutes per hour. And we end up with 2.32622 hours. I think they did 2.32 maybe. Let's see what they said. 2.326. So they went that far. I honestly would not have gone that far if it was up to me. I would have left it like 2.32 or 2.3 hours. So hope that helps.